In recent decades, wastewater treatment plants have undergone a profound evolution. There has been a significant increase in the required removal levels and an expansion of the range of pollutants to be treated. At the same time, increasing emphasis has been placed on process optimization, with the goal of reducing energy consumption and minimizing space requirements. Moreover, today wastewater is increasingly recognized as a valuable resource to be utilized for the recovery of energy and materials. The recent European Directive on Urban Wastewater Treatment, EU Directive 2024/3019, provides clear guidance in these directions, introducing particularly ambitious new objectives. In this lesson, we will analyze these changes, along with the strategies and the technologies currently available to achieve the proposed goals. In particular, we will focus on the implementation of innovative treatment solutions capable of combining process efficiency with the principles of sustainability and the circular economy. These solutions aim to address the challenges related to water and energy supply, the protection of natural resources, and the continuous improvement of quality standards. Among the main challenges related to treatment efficiency are emerging contaminants, organic and inorganic substances present in wastewater even in small quantities, but potentially harmful to the environment and human health. To address this, advanced treatment units are now being used, generally positioned downstream of tertiary treatments. Based on physicochemical processes, these technologies are designed to remove residual microcontaminants, improving the quality of the final discharge and enabling the safe reuse of treated water. The processes used for the removal of these constituents can be divided into two main categories: mass transfer separation and chemical transformation. The former generate concentrated streams that require subsequent management, treatment, or disposal. For example, adsorption involves the saturation of a solid medium, while membrane treatments produce a concentrated liquid waste, also known as brine. The latter are based on redox reactions that transform or destroy the contaminants. Although they require the dosing of reagents or the use of energy, they can theoretically achieve complete mineralization, except in cases of partial degradation. Among the most effective are advanced oxidation processes that use hydroxyl radicals or ultraviolet photons. In recent decades, there has also been a strong push for innovation in biological processes, with the aim of reducing the energy consumption associated with treatments, improving purification efficiency, optimizing space requirements, to enhance flexibility in response to variations in load and flow, and promoting resource recovery. Examples include membrane bioreactors, known as MBRs, and attached growth biomass systems, such as MBBRs. Both ensure a high-quality effluent and compact plant design. MBR reactors, however, involve higher energy and management costs related to aeration and membrane cleaning. Further innovations include aerobic granular sludge reactors and EBPR processes for advanced phosphorus removal. These technologies allow for a significant reduction in oxygen consumption, high sedimentation rates with smaller footprints, and more efficient microbiological selection, thus ensuring high performance. The removal of ammoniacal nitrogen from concentrated streams, such as sludge line recirculation flows, can be optimized using dedicated processes like partial nitritation denitritation or anaerobic autotrophic oxidation with an AMOX biomass, reducing or even eliminating the need for oxygen and external carbon sources. Finally, anaerobic processes are finding new applications not only in sludge digestion, but also in the treatment of high-strength wastewater, offering the advantage of biogas production and a reduction in the amount of sludge generated. This technological evolution reflects a growing trend toward compact, high-efficiency, and circular-oriented treatment plants. In this context, resource recovery, including carbon and phosphorus, plays a central role. An increasingly important aspect in the management of water treatment plants is the minimization of energy consumption and the associated costs. In Italy, wastewater treatment plants account for about 2.3% of the national electricity consumption. About 60% of energy costs are related to aeration in biological processes, 15% to sludge treatment, and 13% to pumping. Achieving energy neutrality is possible through a combination of strategies aimed at reducing consumption and recovering energy. including inventorying the energy use of all electrical equipment, adopting targeted maintenance programs, such as regular cleaning of air diffusers in biological tanks, implementing monitoring and control systems, for example for dosing oxygen or other reagents, recovering the chemical energy contained in the wastewater through aerobic digestion or sludge incineration, when feasible in terms of flow rate and head, recovering the kinetic energy of water using microhydroelectric plants, and finally, recovering residual thermal energy through heat pumps, if the wastewater temperature and local environmental conditions allow. As has been seen, wastewater treatment has now reached a very high level of complexity. In a constantly evolving context, it is necessary to rethink the design, management, and upgrading of wastewater treatment plants with an innovative approach, aiming to ensure efficiency, sustainability, and reliability in the treatment systems of the future.